Welcome to the second lecture in linear algebra series. So in last lecture we had discussed what is matrix and the basic operations on a matrix. So in this lecture we will be discussing the inverse of a matrix and system of linear equations. And so what is an inverse of a matrix? So for a given square matrix, A inverse, which is denoted by using A power minus 1, is a matrix when it is multiplied with A, that is A into A inverse or A inverse into A, we should get an identity matrix. That matrix we call it as the inverse of a given matrix. Inverse may not exist for all the matrices. If a matrix which does not have any inverse, we call those matrices as singular matrices. And a matrix which has inverse, we call it as non-singular or invertible matrices. And so one of the basic conditions for checking whether inverse exists or not is by calculating the determinant. And how to calculate the determinant we had discussed in the last lecture. So if the determinant is not equal to 0, then only the inverse exists. And to calculate the inverse of a matrix, we are going to use some matrix called an adjoint matrix. Now adjoint matrix is calculated by using a cofactor matrix. And we had seen in the last lecture how to calculate cofactors of individual elements. If you write cofactors of all the elements in a matrix form, then it gives a cofactor matrix. And the adjoint of a matrix is the transpose of a cofactor matrix. Let us consider this as a 2 by 2 matrix where we have elements 1, 2, 3, 4. And if you recall, the cofactor is suppose you want to find out the cofactor of 1, just remove the first row and the first column, then whatever the elements that are remaining or whatever the sub matrix that remaining, for that you have to calculate a determinant. Here there is only one element, the determinant is 4, and then we have to multiply with a sign factor, that is minus 1 power 1 plus 1, that is plus 1, so you get 4. 4 is a cofactor for 1. Similarly, for cofactor of 2 is, remove these 2, then you will get 3, minus 1 power 1 plus 2, that is you will get minus 3, and you will get, similarly you will get for this minus 2 and minus 1. And then you have to take the transpose, that means you write all the row elements as column elements and column elements as row elements, that is 4 minus 3 and minus 2 1, that gives you adjoint of A. Now to calculate the inverse, one of the methods is adjoint-determinant method, where you will be finding adjoint A and then divide it with the determinant of A. And as we know the determinant of 2 by 2, we can directly calculate by using A into D minus B into C, and then adjoint A, so we can calculate the inverse. So an example here, for a 2 by 2 3 1 4 2, adjoint A we had already calculated 2 minus 1 minus 4 3, and then the determinant is 2, so we will get this as a inverse. And there is another method for calculating A inverse, that is Gauss-jordon elimination. Okay, so in this what we do is we consider the argument matrix AI, where I is an identity matrix, and then do some elementary row operations, that means swapping of 2 rows or multiplying row by some non-zero scalar, or adding multiples of one row to another row, such that we have to transform this A matrix into I, and whatever the matrix that I is transformed into, that matrix we call it as A inverse of a given matrix. So let us try to understand with this an example. So let us consider this matrix 3, 1, 4, 2, and then we have to augment with 1, 0, 0, 1. So these are matrix that we get 3, 1, 4, 2, and then augment 1, 0, 0, 1. And we can perform the elementary row operations. Our goal is to transform this 3, 1, 4, 2 into an identity matrix 1, 0, 0, 1. To transform 3 to 1, we divide these all the elements of this row by 3. So we'll get 1, 1 by 3, 1 by 3, 0. And then next we have to transform this 4 into 0, because to get an identity matrix it should be 0. So to get a 0, we multiply first row by 4 and then subtract from this. So transform R2 as R2 minus 4R1, and we will get this. And then next one is to get an identity matrix, we have to transform this second row, second element to 1. To do that, we have to multiply by 3 by 2. So all elements of this row by 3 by 2. Then we'll get something like this. And then the next thing is we have to get a 0 here at 1 by 3. But to get a 0, what we do is multiply the second row by 1 by 3 and then subtract from R1. Then we'll get this. And whatever the elements that you have after this I, this is the inverse. So this is how one can calculate the A inverse by using Gauss-Jordon elimination. So the elementary row operations that are allowed are swapping of two rows and multiplying all elements of a row by a constant, or adding multiples of one row to another row. These are also called as row elementary operations. And the next one is the linear system of linear equations. A system of linear equations is a set of two or more linear equations with same variables. Now, a solution to this system of linear equations is a set of values given to those variables such that all equations should satisfy simultaneously. An example of a linear equations is 3x plus 2y equal to 7 and minus x plus 4y equal to 2. So this system of equations has a solution x equal to 12 by 7 and y equal to 13 by 14, for which these two satisfy. Now we are interested in solving this system of equations. Now to solve this system of equations, we can write this in a matrix form. So all the coefficients like 3, 2, minus 1, 4 can be considered as one matrix, that is, we call it as a coefficient matrix, that is, and that can be multiplied with the variables x, y written in a vector, that is a column matrix, and the constant vector that is on the right hand side, we will write it as again a column matrix. So this, now you can see that xy can be calculated by taking this 3, 2, minus 1, 4 to the right hand side, that is nothing but A inverse. So we can calculate by calculating A inverse, and this has a solution when A inverse exists. Now we will see solving this by using one of the methods called the Gaussian elimination method. So in the Gaussian elimination method, what we do is we consider an augmented matrix A, B, and we transform this into an upper triangular matrix. That means all the elements below the main diagonal will be 0. That is what we say it as a upper triangular matrix. And this also we call it as some row reduction, because we apply some elementary row operations like row swapping and multiplication by a scalar, or adding multiples of one row to another row. So once a triangular matrix, once we get an upper triangular form in this A, we can again consider that equation, and then we can do some substitutions to get the values of all the remaining variables. Now let us see. So the first step is we should write an augmented matrix, and second we perform some elementary row operations such that you should get an upper triangular matrix. Whatever the intermediate results that we get, we also call that as some echelon form. And once you get an upper triangular matrix, again we convert that into some system of equations, and we do some substitutions to get the results. Now let us consider this equation where you have coefficients 2, 1, minus 1, 3, minus 1, 2, minus 2, 1, 2, and this is augmented with the b, the right hand side, 8, minus 1, 3, and we do some elementary row operations. First we have to get, so first we consider the first row, first element as a pivot element, and by using that we get a row echelon form. That means all the elements below that first row element should be 0. So to make that, what we do is we multiply row 1 with 3 and then add it to row 2. So R2 plus 3R1 minus 3 plus 3 into 1, so that this will become 0. Similarly for the third row, multiply first row element with 2 and then add it to the third row. Then minus 2 plus 2 into 1, it will also become 0. So if you do on other elements also, we'll get this matrix. The main aim is to get 2 zeros here, because our goal is to convert into an upper triangular matrix where you have all the elements below the main diagonal are 0. Similarly, to select the now we have to select the second row second element, that as a pivot. Before that we should multiply this so that we will get a 1, and then all the elements below should become 0. To make that, what we do is we multiply the second row element with 2 and then subtract from the third row elements, that is R3 minus 2R2, then we will get 0 here also. Now once after transformation, again we will get back to the equation, because now we have here the coefficient of x and the coefficient for the third equation, the coefficient of x is 0 and the coefficient of y is 0. Only we have the coefficient of z, that is also 1. Now once we have the coefficient of z as 1, and here we get, actually when we do this 5 minus 2 into 2, we get actually 1. So z is minus 1. Once we know z is equal to minus 1, we can substitute in second equation so that we get y, and you can substitute in the first equation, then we'll get x as 2. So this is how one can solve the system of linear equations by using Gaussian elimination. First you take an augmented matrix and then transform into upper triangular matrix. Once we have upper triangular matrix, for the last equation we have a coefficient only for the z. By using that we can find out the direct z, and we can back substitute, get the values of x and y. Thank you.